Okay, so regarding your upcoming major test on Sunday, the syllabus from this track will be motion along a straight line, one-dimensional kinematics. So more or less what we have discussed up to last week, but also with some application example questions that we are going to discuss today. Okay. So we were discussing about particularly motion along a straight line with uniform acceleration in the last lecture. And today we will discuss an important special case of that, which is vertical motion under gravity. Okay, so we have discussed about the three equations of motion with uniform acceleration, derivation and applications. Now today we will discuss about a special case of that. Okay, that is vertical motion under the action of gravity. So what happens is that as long as we are talking about vertical motion, where the height from the surface of the earth is not very large, like it's not of the order of thousands of kilometers. Okay, acceleration due to gravity is uniform. So at distances of values that are small compared to the Earth's radius. Radius of the Earth is approximately 6,400 kilometers. Acceleration due to gravity, G, is constant or uniform. It is only when the distance from the surface of the Earth becomes very huge, like of the order of thousands of kilometers, that the acceleration due to gravity starts varying. G is about 9.8 meters per second square, or we also take the approximate value as 10 meters per second square for problem solving. So in this section, we will always assume this, that we are talking about motion at distances from the surface of the Earth, where we can take G as constant. So the first case is free fall, which is very, very simple. That if we were to drop an object from a certain height, so u is equal to 0 at time t equal to 0, an object is dropped at t equal to 0. So it starts from rest. So what happens is, as it falls under the action of gravity at a time t, it will have a downward velocity v. It would have covered a displacement s. So what we do here is we take our axis, our reference frame, we take the axis in the downward direction. Say this is our y-axis. So taking this axis in the downward direction, our acceleration is g cap, or in one dimensional thing we can write it as plus g, and our initial velocity is 0. So applying the equations, we can say that v becomes gt, and the downward displacement becomes half gt square, and v square becomes 2g into s. Third equation. Okay. So these are the equations of motion that we can write with this sign convention and with the application of the fact that the acceleration due to gravity is uniform. Okay. So just make a quick note of this section, and then we will see a numerical example of the above. So if h is equal to 20 meters, g is equal to 10 meters per second square, find the time t at which the object hits the ground below, and find the impact speed. What is the speed with which it impacts? So here, if it hits the ground below with an impact speed vi at a time capital T. So this is a numerical example. Take g as 10 meters per second square while solving this. So just try this question out, people, and send me the answers on the text message. Okay, very good. All the answers are correct. Okay. The time will be 2 seconds and the impact speed will be 20 meters per second. So you can see that for this situation, what we have to do, just a second. Just a minute, people, I will join you. Yeah, just a minute, people. I'll have to restart that software. Yeah, so here we can from the second equation we can see that at t equal to capital T, the displacement becomes the total height, which is 20 meters. So 20 is equal to half into 10 into t square. So from this we will get t as, I mean, technically we'll get t square as 4. Okay. So t should be plus minus 2, but t cannot be negative. So we'll just take t as 2 seconds. We'll neglect the negative root because it's physically not possible. Okay. And for the impact speed, we can either use the first equation or we can use the third equation. Okay, now let's see a slightly trickier type of question. Just a minute, I will join you. Okay. Finish writing this down. Okay, so now let's see a question of slightly more interesting application. So in our next example, again, more or less the same setup, that an object is being dropped from a certain height. So u is equal to 0, it's dropped at t equal to 0. And it's supposed to fall through a height h and impact the ground at time t equal to capital T. Now another guy is observing this from here, and what this person observes, that the object falls through 45 meters in the last second of its motion. Before hitting the ground. Take g equal to 10 meters per second square. So from that, we have to now back calculate, and we have to find what height the object was dropped from, and therefore how much is the total time of its free fall. Okay. So we have to find h. So let me explain what this means. The last second of motion. If a motion starts at t equal to 0, okay, then at t equal to 1, it is here, let's say. Okay. Then t equal to 2, it is here. Then t equal to 3, it is here, like this. Okay. So this journey is happening from 0 to 1 second. So this is the first second of motion. Then this part of the journey is happening from t equal to 1 to 2 seconds. So this is the second second of the motion. Okay. Then this part is happening from 2 to 3 seconds. So this is the third second of motion. Okay. So like that, if this journey continues for some time, and somewhere here at capital T minus 1, and then it's here at t seconds. So this is the last second of motion. Okay, that is the idea of the last second of the motion. It is a time interval between when it just hits the ground and 1 second before that. Okay, so basically what we mean by the term nth second of motion. This is a 1 second time interval from t equal to n minus 1 to t equal to n seconds. This is a concept. So apply that over here and try to work out this question. Yes, Vineet and Tavish, your answers are correct. So see, this total displacement at t seconds is equal to h. Okay, but if we were to see at t minus 1 second, this would be the displacement. Let's say this is also unknown, but we know that the difference of these two, this is the displacement in the last 1 second, and this is 45 meters. Okay, so displacement after t seconds is half gt square. Displacement after t minus 1 seconds, okay, and the displacement in the last second is the difference of these two, and that is given to us as 45 meters. So we have this equation. So when you solve this, from this you will get t is equal to 5 seconds, and which means that the impact speed will become 50 meters per second.
If it were asked that the person observes that the object falls through 45 meters in the last 2 seconds, then would we have taken t minus 2 in that equation?
Yeah, correct. We would have done that. Like any amount of time. Suppose it said that it travels 100 meters in the last, suppose 3 seconds. So we would have taken like this, that s at t minus s at t minus 3 is 100 meters. Okay. So half gt square minus half g of t minus 3 whole square would have been 100, and then we would have solved this for t. Understood now?
Yes, sir.
Okay, so hope this question is fully clear. Now we come to another variation of free fall motion under gravity, and that is that instead of the object being dropped, if it is thrown down, okay, so you can take this as a second example of free fall. So if we have this situation now that it throws it vertically down with some initial speed, okay, and then it goes and hits the ground. So here at some intermediate time t, if it has a speed v and it has made a displacement s. So again, what we'll do is we'll take our axis downwards. Okay. So we'll take our initial velocity with a plus sign, our acceleration with a plus sign. So in general, v as a function of time will become u plus gt. Displacement as a function of time will become ut plus half gt square, and p square will be equal to u square plus 2 gs. Third equation. Okay. So for example, suppose we have this situation that in the above case, a person at a height of h equal to, let us say, 300 meters above ground, throws an object at u equal to 20 meters per second down at t equal to 0. Okay. So we want to find, first of all, the velocity and displacement after, let's say, 2 seconds. And we want to find the time capital T at which it hits the ground. Okay. And we want to find the impact speed with which it hits the ground. So you can see that we have to just apply the above equations. Okay. But with the initial velocity being there, the solving is a little bit more tricky for time because it's a quadratic equation which you have to solve now. So just try this out. Substitute in the appropriate equation to get each of these things. Okay. The first part is direct substitution. Just at t equal to 2 seconds, you have to again take g as 10 only. Okay. We'll take the value of gravity. In most questions, we'll take it as 10 for convenience, but actually it is 9.8. But one thing you should keep in mind is if you're solving any question from the standard reference books like H.C. Verma or D.C. Pandey, etc., unless the question gives you that take g as 10, you should take g as 9.8. Okay. If nothing is mentioned about the value of g, you should take it as the more accurate value of 9.8 meters per second square. Only where the question specifically mentions that you can take the approximate value of 10, there you should take 10. Otherwise, you will get some variation in the answer compared to the answer key. Okay, so got the first part, anyone? At 2 seconds, what is the velocity and what is the displacement? Yes, Tavish, that's correct for velocity. Yes, Manav, both your answers are correct. Good. Tanay, you have to check your second answer. Achha, that is the no. Okay, so I'm just putting up the answers. Okay, so this thing, the velocity after 2 seconds will be 40 meters per second, and the displacement will be 60 meters after 2 seconds. This thing, the time when it hits the ground should come out to be 6 seconds, and therefore the impact speed come out to be 80 meters per second. Okay, so let's look at the solution of each part. So here in general, we will take US plus 20, ES plus 10. So my general equations of motion become that V is equal to 20 plus 10t, S is equal to 20t plus 5t square, and V square is equal to 20 square plus 20s, like this. Okay. So at t equal to 2 seconds, P will become, that's how we get this 40 meters per second, and S will become, that's how we get this as 60 meters. Okay. Now second part, at t equal to capital T, S should be equal to, how much is it? H, which is 300 meters. So from the second equation, so this quadratic equation has to be solved for time. You can't take a negative time, that becomes answer. So the time is 6 seconds. And therefore the impact speed You can also factorize this. Okay, instead of using the discriminant method, you can directly factorize this and see that okay. So people hope this question is fully clear.
Yes, sir.
Okay. Now we move on to the second situation of vertical motion under gravity, which is not free fall but vertical projection. That is when we throw an object upwards. Okay. So vertically projected. A projection or projected motion means when we are throwing something. Okay. So the standard situation here is from the ground level. If we assume that we are throwing an object upwards, straight up, at an initial speed u at t equal to 0. So what we know is that this object will go up in a decelerated motion because of gravity acting. Then at some stage it will stop for an instant and then it will come vertically down. and it exactly retraces its path and returns back to where it started. Okay. So in this case, what we do is we take our y-axis upwards, or our reference frame upwards, and our origin at this point. So the moment we do that, our initial velocity comes with a plus sign, but our acceleration comes with a minus sign, because you can see that the initial velocity as a vector is uj cap, but acceleration as a vector is minus gj cap. So when we write these vectors in scalar notation, you can see it's this. So at some time t, if the particle has reached here, its velocity is v, and its displacement from here to here is s. So we can see here that velocity as a function of time will become u minus gt. Displacement as a function of time will become ut minus half gt square. And the relationship between displacement and velocity will be this third equation. Okay. So therefore, when it reaches the highest point, what happens is when it reaches here, momentarily we know its speed is 0. And this is called the maximum height. So at the position of maximum height, h, the displacement has become h, and the instantaneous velocity is 0 because it stops momentarily and then descends. So basically, it ascends to the maximum height, then stops momentarily at that position. So at the maximum height position, it stops momentarily and then it descends downwards. So that is why v is equal to 0 when displacement is equal to s. So now using equation 3, see that v is equal to 0 when the displacement is equal to the maximum height. So 0 is equal to u square minus 2gh. So this gives us a direct formula for the maximum height. And as expected, it depends on how much initial speed we have given. It depends with the square term. So for example, if a certain speed is giving us a maximum height of 20 meters, if we double that speed, the initial speed, we will get a maximum height of 4 times. So we'll get a maximum height of 80 meters. So just note down up to here, then we'll also write down the formula for the total time of the motion, that is the time taken to go up and come down. And we'll see what about the impact speed also when it comes back and hits the ground.
Sir, done.
Right. Okay, so this is one important formula. The maximum height is u square by 2g. Now the next thing we'll see is that the time taken to reach maximum height. Okay. So v is equal to 0 at t equal to u by g. This comes from equation 1. So this is the, you can say this is the time of ascent. So if you projected the object from the ground at t equal to 0, then it will reach the maximum height position at a time of u by g and at a height of u square by 2g. So this is the ascent part of the motion. Now the second part of the motion is the descent. So from that point onwards, it now starts descending and finally hits the ground again from where it was projected at t equal to 0. At some time t. So the total time of what we call flight, that is ascent plus descent, that is the time at which it returns to the starting point or the point from which it was projected. So this time we want to calculate. So displacement is 0 at t equal to capital T. So from equation 2, you can see that. So as you might be expecting, this time will be double of this time when it reaches the maximum height. So obviously t equal to 0 is the root we will reject because that is the initial time, and t is equal to 2u by g. So this quantity becomes the total time of flight. So this here is 2u by g. So you can see that the ascent and descent are symmetrical in time. So basically from t equal to 0 to t equal to u by g, it is ascending, and then from t equal to u by g to t equal to capital T, which is 2u by g, it is descending. So this time is actually half the total time of flight. So if you throw an object upwards and it comes back to you, you catch it again after 6 seconds, then you can be absolutely sure that it has ascended for 3 seconds and then descended for another 3 seconds. Yes, Jitesh, you have a question?
Sir, can you explain this second wala again? I didn't get it.
Total time, no? See, when it comes back to the starting point, you threw something up, it went up vertically, and then eventually it will come back to where it started, no? So at the moment when it comes back to where it has started, what is the displacement? It is 0, no?
Yeah,
So
displacement
now
is
what
zero.
is so now what is the relation between displacement and time? S is equal to ut minus half gt square, no? The second
Yes,
equation. So
yes,
in
sir.
that you put the displacement as 0. So that will give you the time when it's come back to starting point, no?
Okay, so only this is there.
Yes, only that only. Huh? We are just substituting s equal to 0 in the second equation to find the time when it returns to the starting point.
Yes, sir. Got it. Thank you, sir.
Sir,
Yes, yes, beta.
sir, in the red part, what you have written, the second part would be t equals to 0 to t equals to t, right?
T equals to
After this,
0
after this.
to T. नहीं, descent वाला है देखो. From U by G to capital T, that is from capital T by 2 to capital T, it is descending.
Okay,
Whereas
sir.
from zero, got it, no? So that
Yes,
arrow
sir.
is showing that it's the descent time. Okay.
Yes, sir.
You can write in bracket over there that that's the time of descent, and the first part is the time of ascent. Okay. Okay. Now the final thing, the speed at which it impacts. Now logically you can understand it will be the same speed. You can just think in terms of work energy also, no? Because it's come back to the ground level. So its potential energy is again zero. So its kinetic energy should be the initial kinetic energy. But here we'll show it from kinematics. Okay. So at T equal to capital T, which is 2U by G, this velocity is the impact velocity. So V impact will be equal to U minus G into 2U by G. So as expected, it is equal in magnitude but opposite in direction. Okay. So two important things we learn from here, that the time of ascent and the time of descent are the same, which is half of the total time of flight. And the second thing is that it comes back to the starting point with the same speed, but obviously in the opposite direction. So impact speed is equal and opposite, equal in magnitude and opposite in direction to the projection speed at t equal to 0. Or actually, since we are talking about direction also, we will say velocity. Okay. So now also sometimes what is useful here is to analyze the graphical representation of velocity versus time, and side by side also understand the graphical representation of displacement versus time. So last time we had talked about these kind of graphs with uniform acceleration. So this is just a case of application of that. So velocity versus time, it represents this relation v is equal to u minus gt, but up to a limited amount of time, and that time is the total time of flight. So v is equal to u minus gt. So it starts with the velocity plus u. Okay. At the time capital T by 2, which is u by g, the velocity becomes 0. And at exactly double of this time, which is the total time of flight, 2u by g, the velocity becomes minus u. And that is when it has hit the ground. And similarly, the displacement is representing this equation, ut minus half gt square. So it starts ascending, but with decreasing speed. So the slope is decreasing. Then momentarily it stops at the top. So that's the local maxima. And then it starts its descent. So it finally hits the ground at total time t, which is 2u by g. But at the exact half time, it reaches the maximum height position, where h is equal to u square by 2g. So this graph is also useful in analyzing problems which are other than just the direct formula based questions for maximum height and total time. Yes, Jitesh, you have a question, beta?
Sir, and here the time of ascending is equal to time of descending, or they both are like time of descending is greater than time of ascending.
No, they're same now, beta. You can see that the time of ascending is 0 to u by g, na? And then
Yeah.
descent is u by g to 2u by g. So they're exactly the same amount, na? These
Okay.
graphs are symmetrical, na? So the motion is divided exactly into two equal halves as far as time is concerned. The first half is the ascent and the second half is the descent. Okay, now the other thing is there is a symmetry in the motion, okay, which we have to understand. That is, I mean, it's not just that the time is divided equally, but even the way the motion happens, okay, the second part of the motion is like an exact mirror image of the first part of the motion. So let's understand that. The symmetry in ascent versus descent. So if we project it at t equal to 0 with an initial speed of u, okay, and this is the first part of the motion where it's ascending until it reaches the maximum height position at t equal to half the total time, which is u by g. The velocity becomes 0 and the displacement becomes h. Then after this, it starts descending. So I'm showing it as a parallel line, but actually this line overlaps with the first line. Okay. And actually this position is exactly the same where it lands. So the impact velocity becomes minus u at time equal to capital T, which is 2u by g. Now the symmetry is such that now if I were to observe that during the ascent, it was somewhere here at t equal to, let's say, some t1. Okay. It has a velocity plus v1 and a displacement equal to s1. So this is v1 and the displacement is s1. Now I'll observe that during the descent also it will reach here at some point of time. So at this point of time, the velocity will be exactly minus v1. Okay, and the displacement will still be plus s1 from the ground. So in that case, if the time is t2, this t2 will be such that t2 is equal to capital T minus t1. This is the symmetry. So let me show this with an example. So suppose we project something from the ground at a speed of, let's say, 50 meters per second at t equal to 0. Then we know from the above calculation that it will reach the maximum height at 5 seconds. Okay, and that maximum height will become 125 meters, taking g as 10. Then it starts its descent. So we know that it will hit the ground at capital T equal to 10 seconds with an impact velocity of minus 50 meters per second. Okay, but if we were to observe in this, suppose at t1 equal to 2 seconds, we want to find out v1 and we want to find out s1. And then again, I will take a second time t2 equal to capital T minus t1. So that is 8 seconds. So if I compare what will be the velocity at this time and what will be the displacement at this time, you will observe this symmetry. Okay. So write down this part about the symmetry and then apply it to this. Okay. So I just want you to find out these things yourself and verify this symmetry that will work. That because I have taken the second time as exactly total time minus the first time. So this was 2 seconds. The first time is 2 seconds after start. The second instant I've taken is 2 seconds before it returns. So there is that symmetry. So there'll be the symmetry in the values of velocity and displacement also. Okay. But however, you should verify it from the equations. Okay. Then you will understand the logic of this symmetry that I'm talking about here. Okay. So just note down this aspect of symmetry in the first part and then work out the values of V1 S1 and V2 S2 so that you see how that symmetry actually works with a numerical problem. Yes, Vineet, very good. That's correct. So if you use these standard equations, so for this particular case, you're taking U as plus 50 and A as minus 10. So your V will be 50 minus 10t and your S will be 50t minus 5t square. So if you use these equations, you will get V1 over here as plus 30 meters per second and S1 as, what was it, 80 meters, right? Okay. And you will get V2 as minus 30 meters per second. So you can see that V2 is minus of V1. You get S2 as again 80 meters. So S2 is equal to S1. So this is happening because this time T2 is equal to capital T minus T1. Okay. T1 was 2 seconds. That is 2 seconds after start. Okay. And T2 was 8 seconds. So that is 2 seconds before impact again. So there is the symmetry in the two times, and that symmetry is reflected in the values. So if in the diagram this is 2 seconds. Okay. Then this is where it will be on its way down, exactly at the same position. Okay, actually it's the two lines overlap, the ascent and descent line. It is only for diagram purpose that I'm showing it as. So this time will be exactly 8 seconds. So it took 2 seconds to go from initial to this position. So it will take 2 seconds to go on its way down from that same position to ground. So that is the symmetry. So this symmetry is important to remember. That symmetry you can see reflected in the graphs here also. Okay. See that if this is some time t1, then here this time t2 will have that symmetry, that t2 is equal to capital T minus t1. And that is when their displacements are the same. And that same thing is reflected in this graph also. If this is the time t1 when the velocity is plus v1, then if you take another time t2, which is capital T minus t1, so this is symmetrical to that one. So you'll see that at this time, the velocity v2 will be minus of v1. So that same symmetry is reflected in the above graph also. Okay, so people hope this part is clear. Now for this same data, this same question, we will solve another aspect. So that same example, vertical projection from the ground with a speed of 50 meters per second at t equal to 0. We have to find displacement and velocity at t equal to 4 seconds, t equal to 5 seconds, and t equal to 6 seconds. Okay. And second, we have to find distance traveled from 0 to 4 seconds and from 0 to 6 seconds. So just try this out. So the first part is formula based. The second part is only where we have to be a little bit careful. Again, take G as 10 meters per second square. So it's the same data as the previous question. Just a different set of things you have to calculate.
So the total time of the flight is 10 seconds only, or
Okay, very good. So I'm just putting up the answers here. So you'll see that at t equal to 4 seconds, the velocity will be plus 10. That means it's going up with a velocity of 10. And the displacement will be 120 meters from the starting point. Okay. At t equal to 5 seconds, the velocity would have become 0. And the displacement would be equal to the maximum height, which is 125 meters. But at t equal to 6 seconds, the velocity is now, by that symmetry also you can see, as well as by calculation. So it's on its way down, but the displacement is 120 meters only. Okay, because always the displacement is from starting point, from the start. So it's come back to this point. Okay, so it's like that. Whereas that is why when you talk about the distance traveled, here this is 125 meters, but he, sorry, 120 meters. Okay. But here the distance from 0 to 6. So what is happening is from 0 to 5 seconds, it has a displacement of plus 125. But from 5 to 6 seconds, its displacement is minus 5 meters. So the total distance from 0 to 6 seconds will become 125 plus mod of this minus 5. So 130 meters. Okay. So this is 130 meters. It's going 125 meters up from 0 to 5 seconds. Plus it's coming down 5 meters from 5 to 6 seconds. That is the thing that we have to be a little careful about. Okay, very good, Jitesh. You got the answers. Vineet, correct. So to answer a question like this, now we have to understand that the total time of flight was 10 seconds. Therefore, ascent was from 0 to 5 seconds and descent was from 5 to 10 seconds. So therefore, the distance from 0 to 6 will become mod of displacement from 0 to 5 plus mod of displacement from 5 to 6. We have to break this up because this one is plus 125, but this one is minus 5. So we have to do this step. Do a couple of more. Yeah, so we'll do a couple of more examples of
So,
yes.
we found that distance from 0 to 6 is 125 plus the mod of 5 equal to 130. Sir, why are we
Yes. Why are we?
doing mod of 5 minus 5?
because we are calculating distance now. So if we don't take the mod, we'll get the displacement now. It will come back to be 120 now. You understanding now?
Yes, sir.
Displacement is the shortest path from initial to final. So if something went up 125 and then came down 5, what is the straight line between the initial and that? It's only 120 meters. But what is the actual path length traveled? The actual path length traveled is 125 plus 5 now, because it also came down through a distance of 5 meters. So that is the difference between displacement and distance now.
Yeah, sir. Got it.
Got it now? So why we took mod over here now?
Yes, sir.
Okay. Okay, so this is done. Now let's conclude this vertical motion section with one last type of question, which is a bit of a variation on this question. Okay. So suppose we have this situation again, that so from a height of 150 meters, an object is projected upwards now. So at t equal to 0, an object is projected upwards at 10 meters per second, and g is equal to 10 meters per second square. So it goes up and then eventually it descends. And on the way down, suppose the person doesn't catch the object. So eventually it comes and impacts the ground. Some time t. So we have to find the total time, the impact speed, okay, and the total distance traveled. Okay, so anybody got the answer yet? So here, just a word about the reference frame. Again, what you can do is you can take the y-axis upwards only because the motion starts upwards. Okay, and take this point as the origin where it starts. So at t equal to 0, the initial velocity will write with the plus sign. Okay, but the acceleration is minus g. So minus 10 meters per second square. Per we have to check your answer. Okay.
Sir, and final velocity is also 0.
Final velocity is
0.
no, but when it hits the ground, no? Only
No,
impact
no,
with
only in the ascent part.
at the highest point, yes, final velocity 0. Okay.
So then we
So
can take the highest point as the new reference, and then we can calculate the descent.
you can do that, but that is actually not required. You can use the same reference frame, and you can see that what is happening at t equal to capital T. What is the displacement going to be? It is going to be minus 150 meters, according to this reference frame.
Yes,
Right?
sir.
Okay. So now just use the equations. So your standard equations from this is that velocity as a function of time is 10 minus 10t, and displacement as a function of time is 10t minus 5t square, and v square is equal to 10 square minus 20s. Okay, so all this we can use. So now substitute this. Okay, so in the second equation you put minus 150 is equal to 10t minus 5t square. So from this you can find the value of time. Once you found the value of time, put it in the first equation, so you'll get the impact speed. Okay, or you can use this third equation also for the impact speed. Use equation 3. Oh, sorry, this will be minus 150. No? You'll put S as instead. Okay, so anyhow, let's solve this equation. So we'll get t square minus 2t minus 30 is equal to 0. So we'll take t as square root of 31 plus 1 second. Now square root of 31 we can calculate by method of binomial approximation, which I am showing above over here. Root 31 we can write as square root of 36 minus 5. So that is 36 minus 5 to the power half. So that is approximately 1 minus 5 by 2 into 36. Okay, so per, I think maybe some small numerical mistake in your calculation, or you forgot to add the 1, maybe, I don't know. So impact speed is square root of 3100. Okay. Okay, so people hope this question was fully clear. So with this, we complete vertical motion. Okay, so next week we will start with the second part of kinematics, which is two-dimensional motion, in which we look at. So I'll send you a list of questions to do from the module as well as from HC Verma kinematics chapter for one-dimensional motion, plus a worksheet of guideline questions. Okay, so do that by the end of this week so that you're prepared for the major test coming up. Yes, Parv, you have a question, Beta?
Yes, sir. Sir, here
Okay.
you have taken the like reference where the man is standing.
Yes.
Okay, sir. Sir, but
I've taken the origin as the point of projection, okay, and the y-axis in the upward direction. I could have taken the reference on the ground also, but then the initial position would have been 150, na? And the final position would have been 0. So the displacement would have still been minus 150.
yes, sir. Okay, sir.
Okay. But the logical thing generally to do is to take the origin as the starting point of the motion, okay, and the direction in which the object starts moving at t equal to 0, that you should take as the positive axis. So
Okay.
there's no hard and fast rule, but that will be the most natural way of selecting the reference frame, right? Okay, so hope this is clear. That's it for today's class then, people. Wish you all the best. Have a nice day.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir.
sir.
Bye.
Bye, sir.
Okay.